Hey everyone, so up until now we've pretty much only dealt with stuff moving in a straight line. But, what about a curveball or the Earth going around the sun? That's where things get really interesting. Today we're doing a big picture review of Chapter 4, all about motion in 2 and 3 dimensions. Let's get right into it.
So here's the game plan. First, we'll talk about why we even need to move beyond straight lines. Then, we're going to build our physics toolkit, starting with the must-know vocabulary and then the key equations that make it all work. Finally, we'll tie everything together and see how these concepts play out in the real world. Think of this as your go-to summary for the entire chapter.
So far, our physics journey has been on a pretty narrow track, just back and forth, one dimension. But the real world, it's way more complex and frankly way cooler. This chapter is all about breaking off that single track and learning how to describe motion in the full 2 and 3 dimensions that we actually live in. And this quote just says it all, doesn't it? I mean, think about a football spiraling through the air, a jet doing a loop-the-loop, or even our own planet making its yearly trip around the sun. Pretty much nothing truly important moves in a perfectly straight line. The universe is full of curves, and this chapter gives us the tools to finally understand them. And here's the great news. We're not starting from square one. Not at all. We're just taking the ideas we already know, like position, velocity, and acceleration, and giving them a serious upgrade. We're going to expand them into 2D and 3D using the power of vectors. It's like giving our old tools a new superpower. All right, let's get our toolkit started with the vocabulary. I mean, you can't really solve the problems if you don't speak the language, right? I'm going to put the key terms up on the screen, so definitely feel free to hit pause and let them sink in whenever you need to. Okay, so this first batch of terms really lays the foundation. You'll see some familiar faces here, like acceleration and displacement, but notice they're now defined as vectors. That's the key for thinking in 2D and 3D. We're also introducing a couple of new terms that are absolutely essential for anything that spins or turns: angular frequency and centripetal acceleration. We'll be seeing those again in a bit. Now, this next group gets us a little closer to some real-world action. We've got terms specifically for analyzing things flying through the air, like projectile motion and range. But honestly, the most mind-bending idea here might be the reference frame. It's this reminder that how we see motion totally depends on our own point of view. And to wrap up our vocab lesson, we have these last few terms. Time of flight and trajectory are pretty much what they sound like. They help us map out the entire path of something that's been launched. Keep all these terms in your back pocket because you're about to see them show up in the equations. All right, we've got the language down. Now let's move on to the second part of our toolkit, the key equations. This is the math that lets us actually analyze and predict all this complex motion. So, full disclosure, there are 22 key equations in this chapter. And I know that sounds like a lot, but don't worry, we're going to flash them all up on the screen, grouped together, so you have a complete reference. Think of it as your formula cheat sheet for this whole topic. This first set of equations should look pretty familiar. We're essentially taking the concepts we already learned for one dimension and just rewriting them in the language of vectors. You can see the equations for the position vector, average velocity, and instantaneous acceleration. This is our bedrock. Now, this next batch gets a little more specialized. This is where those new terms we learned really start to shine. Check out the formulas for time of flight and range. Trust me, these two are the workhorses for solving just about any classic projectile motion problem you're going to find. And we're also starting to see the math for circular motion come into focus. And our final set of equations wraps things up by covering the last two big ideas: circular motion and relative motion. You can see how we calculate the different kinds of acceleration when something's turning. And then, those last three equations, they are the absolute key to translating motion from one person's point of view to someone else's. Okay, on to our final section. We've built our toolkit, we have the terms, we have the equations. Now let's see how they actually get applied. This is where everything clicks into place. So the first big concept is that we now treat everything as a vector. But look, the most important takeaway here, the one thing that unlocks this entire chapter, is this: motion in perpendicular directions is totally independent. What a ball is doing horizontally has absolutely nothing to do with what it's doing vertically. Getting that concept is everything. And following that exact same logic, acceleration is a vector too. The relationship we learned way back when still holds true. Acceleration is just the rate of change, or if you're in calculus, the derivative of the velocity vector. What's cool is this means we can take our old familiar kinematic equations and just pop them into vector form to handle any direction. And that leads us right into projectile motion, which, by the way, is just a fancy name for an object flying through the air with only gravity pulling on it. And this is where that whole independence idea becomes a superpower. We can analyze the horizontal part, which has zero acceleration, and the vertical part with constant downward acceleration as two separate problems. It turns one complex, curved path into two simple, straight-line problems. Next up is circular motion. When an object is moving in a circle at a constant speed, that's uniform circular motion, its acceleration is called centripetal acceleration, and it's always pointing right toward the center of the circle. Now, if the speed is changing, we also have something called tangential acceleration. The total acceleration is just the vector sum of those two put together. And finally, we have relative motion. The big idea here is that there's really no single correct speed for an object. It all depends on the observer's point of view or their reference frame. Think about it. If you're walking on a train, your speed relative to the train is different from your speed relative to someone standing on the ground watching you go by. The equations we saw give us the exact method to translate between those different points of view.
So there you have it, our whirlwind tour of motion in 2D and 3D. It's amazing how the simple tool of a vector lets us describe everything from a baseball in flight to a spinning planet. Which kind of leaves us with one last thought. Now that you've seen the physics behind all of them, which type of motion do you find the most interesting? The elegant arc of a projectile, the constant pull of circular motion, or the brain-twisting puzzles of relative motion? Something to think about. Thanks for watching.